So in this video, we're going to be using Python to plot isothermic curves for water. We're going to be graphing pressure versus specific volume of water. And to do this, we're going to be using the generic cubic equation of state. Since there are different versions of doing this, we're going to keep it simple and use the SRK version. So if we look at our generic cubic equation of state here that I have in front of you guys, you can see that there are 4 coefficients that are going to be very relevant when we go to graph our pressure on the y-axis and our specific volume on the x-axis. But before we get into Python and getting all that data and plots, we need to find what those coefficients are, because they're going to allow us to bring in other properties of water that we're going to need. So if we scroll down here, I have some other equations pulled together. These are all going to be useful for us in creating a function that can compute the coefficients in the original cubic equation of state function. So now we can jump into the Python part of things. I've gone ahead and prepped some of the code for us. It's just basically importing some data and pathways, just generic things that we're going to be using throughout our code. I included our R value because that's going to be referenced quite a bit, and then I included this che.props, which is going to bring in data from ChemCAD specifically about water, which I have specified here. And we're going to use these properties of water throughout our code, and it'll just make life easier on us instead of looking up values for all the properties of water. So I'm going to start us off by defining a function for our cubic coefficients. So say define, I'm just going to call it cubic C, and I'm going to specify temperature here because our temperature is going to remain constant because our isothermic curves are going to have constant temperature in each of them. So this is going to be useful in defining coefficients, especially A, because A is going to be dependent on temperature. If we come back to our cubic equation of state here, we see that A is dependent on temperature. So if you also look at our equation here, we can see the 4 coefficients that we're going to want to be defining, which is A, B, epsilon, and sigma. So we can go ahead and enter that into our code as well as our return. A, B, I'm going to call epsilon E and sigma S. So we have that. Now we can start looking at these other equations that we have. I'm going to go ahead and split this screen so we can see the equations and the code. Alright, so we scroll down and find an equation for A. We have one right here. And we see we have this psi figure times alpha that's dependent on the reduced temperature times a lowercase omega r squared, the critical temperature squared, all over the critical pressure. So you're probably wondering what this psi character is here. So if we scroll down even further, it gives us a nice chart that gives us values for psi, also for omega, epsilon, and sigma. Goodness. Okay. So we can go ahead and put in some of those values, and we're specifically looking at our SRK section here. So that's going to be along this line. So we can define sigma, which is our S. It's going to be equal to 1. Our our epsilon, E, is going to be equal to 0. Why does it keep doing that? Okay, and then our psi is going to be 0.42748 So now that we have those values in there, we can go back to our A equation, and the reduced temperature here that alpha is dependent on, it gives us a nice equation here of what that is, which is just temperature divided by the critical temperature. And since our temperature is remaining constant and the critical temperature is nicely given to us in the hw properties of water, we can go ahead and make an equation for that. So we'll call it TR is equal to our temperature divided by, and to bring in the properties from our hw tools, we do P dot TC, the critical temperature. So the next thing that we're going to want to look at is finding this alpha value here. So if we scroll down again, it nicely has an equation for what alpha is going to be in our SRK equation. So we can go ahead and include that. I'm going to call it alpha because it's different than our A. So that's going to, we notice that the whole thing is squared, so I'm going to go ahead and do that just so we don't make any mistakes. And then we have, I'm going to go from right to left just because it's easier for me. So we're going to have 1 minus our reduced temperature to be 0.5 power. And then we'll have 0.48 plus 1.574 times our omega. So we're going to bring in the properties from CHE props of our lowercase omega because that's already stored in that data. So P dot lowercase w, and then minus 0.16176 times omega squared P dot w this should not be kept. This needs to be okay. That's squared. We need another parentheses. All right, and then 1 plus. I think that should be good. Looks like we're ready to write the equation for A. So we can go ahead and do that. Say A equals psi times alpha times, and our R value we already specified, so we can just do R times R times our critical temperature, which we define P dot TC. And that's all going to be divided by our critical pressure. So that's also going to be specified by the CHE props. Okay, so now if we look at our B equation up here, the only thing we don't have is this omega right here. So we come back down to our table, you can see that it gives us that value right there. So we can go ahead, oops. Ah. All right, goodness. All right, so we can define omega 0.08664, and then we can go ahead and write out the equation for B also, which is just going to be omega times our R value times our critical temperature divided by our critical pressure. Alright, so I made a couple errors up here in my syntax, so I fixed those, and now we have values for A, B, E, and S, epsilon and sigma. So now what we want to do is make a function that will compute our pressure values for us. So these are going to be dependent on the specific volume and temperature, which for temperature we used above in our cubic coefficient function up here. So we'll define this one as cubic, I'm just going to call P for pressure, and it's dependent on volume and temperature. So from above, up here, we already defined A, B, E, and S that were values dependent on temperature, so we can go ahead and bring those values into our function down here. So we'll say A, B, E, and S are equal to our cubic C. And then we need to return the pressure values. So we can either write out the equation for pressure just in the return box here, or we can make set up a variable for it in the equation and then return the variable, but it's easier to just put in the equation, so I'm going to do that right now. And that should be good. All right. So now we're about ready to plot some isothermic curves. So to do that, we'll need values for volume, since our plot is going to be on pressure versus volume axis. I've already imported numpy and plotly up here to get us ready. Plotly, subplots. So we'll be using those. So we're going to define our V first. Linspace. I'm sorry, we need to do numpy linspace. This is going to give us linearly spaced specific volume values. And so we need to specify a range. We'll go 0 to 600, and we'll say there's 300 points. And the other one we need is pressure, which we already have from our defined cubic P right here. That's defining our pressure values. So we can just call that P cubic P. And we need to start with some kind of temperature because our temperature is not defined yet. So I'm just going to make it 300 because that's what we used to check it above in the last one. So now we can start making our plot. So we'll have a figure equal to make subplots. Next, we do fig add a scatter to add our scatter plot. So we need to define what our x and y variables are. So our x is going to be the volume, and our y is going to be our pressure. And we can define some kind of mode for this. I'm going to make it markers so that way we can see the individual points on our graph. So here we have our plot of volume on the x-axis and pressure in the y-axis. And these are points here, the temperature points. But I've pulled up van der Waals isotherms, and you can see here that they have this little dip right here. And in our graph over here, we don't have that. So we're gonna need to do some changes to this to get it to look like that one. So one issue we could be having with our graph here is that we're starting on 0 down here, which I believe these isotherm curves don't start at 0. And if we look back at our equation of state here, the first term we have in the denominator, there's V, our volume, minus the excluded volume. So if we set our initial volume to be 0 on our chart over here, that's going to give us either a negative in the denominator or 0, and we don't want either of those. So we can go ahead and change that. So we want to make it larger than b, so we have a positive number in our denominator. So I'm just going to say 1.05 times b. And since b up here is, where's b? Here it is local in this function here, we need to bring it down into what we're doing so that it can recognize it. And we're also going to need to bring in omega. All right, so we can go ahead and do that, see if that helps. So that helped a little bit, but now we have this huge gap here between this point that has a really high pressure and all the way down here with really low pressure. So an easy way, when we have a big jump like this, an easy way to look at it as something that is more representative of what the points actually are is that we can do a logarithmic scale instead of a linear scale here. So to do that, I'm going to do fig update. And we want to update our x-axis. And what we're updating is the plot type. We want it to be log instead. Uh-oh. Oops, can't spell. Axis, not axis. No? There we go. So this is getting a little bit better. We can see a few more points now, but still not great. So what we can do is change our linearly spaced points here to be logarithmic scale also. When we do this, we also need to change our starting value to be log NP log of that. So that way it gives us an accurate value for our starting point. So it's not taking the log of 1.05 times b. And I did something wrong here. Hold on. Oh, we need to change this scale. This needs to come down a lot to, let's say, 2. Let's see if that's better. Why is it upside down? What if we go ahead and update? Go ahead and change the range. Update. Can't spell, goodness. Update y-axis. We'll want to change the range to be, let's say, -5 times 10 to the 8th to 5 to the 8th. I think I found my issue. We needed the log base 10. There we go. So now we can see this dip right here very well. There we go. We can change our number of points or our markers to a line. And there we go. We have a really nice curve here. We can even shorten up this length here. We'll say instead of 2, we'll do -2. There we go. So now we have a really nice isothermic curve right here. So now that we have our isotherm curve here, this is just for our temperature at 300 Kelvin. We have one thing left to do, almost done. Since this curve here is just for 300 Kelvin, goodness, we want to make multiple different isotherm curves, just like in our photo over here, how there's multiple curves at different temperatures. So that's what we're going to be trying to do right now. So to do this, we need to make a for loop for our temperature values. And in doing this, it's going to give us the opportunity to specify like how many curves we want and show many different isotherm curves on the same graph. So we are going to, I'm going to put it under this one, say T for T in range. So we need to specify our range here, what temperature we want to start at and what temperature we want to end at, and the step values between those temperatures. So I'm going to start at 250 Kelvin, just a little bit below freezing point, and go, if, let's say we want it to be in 25s. So after 250, we would have 275, and then 300, like that. So if we want it to end on, say, 750 Kelvin, we would need to put 775 because Python is weird like that. Doesn't include the last one. So then we need to add in our pressure. So I'm just going to move that down here. And we also need to include our scatter plot in there so it runs through there. Another thing we can do is name our temperature values so that it shows the temperatures along the column of lines. So we attach an F string, T equals, it's going to be our temperature. And that's just going to say like T is equal to, and then pull in the temperature values from our for loop here. So here we go. We got our multiple isotherm curves. And cool thing, we can add and remove them if we like. Just take them out, put them back in. There's many things we could do to change this up even more, but I think we're at a good spot right now because we can see there's a clear dip here, like in the other one here from Wikipedia. So yeah, if we zoom in here, we can even see it a little better, those curves. I don't know how to zoom back out. That wasn't it. Okay, well, we're done anyways, so that's okay. But hopefully from making these isotherm curves, you understand the cubic equation of state a little better now. Thanks for watching.